In this video, we are going to finish the chapter discussing infinite limits and limits at infinity. Here, the goal is to be able to operate with the extended real number system, okay, including infinity and negative infinity. And I just wanted to recall, what does it mean for a function, a real function, to go to infinity as t tends to x? Okay, that means that for every number n, there exists a delta such that if x and t are close, x and minus t in absolute value is less than delta, then f of t is bigger than n. Remember, this is the type of situation. Let's do a picture here. This is a type of situation where we have a vertical asymptote at x. Okay, would be something like this. And then what we are saying is that whenever x is within, whenever we take some value n, okay, there will be some delta that guarantees, okay, that the values of the function are larger than n, okay? That is a vertical asymptote at x. But then we have also the horizontal asymptote, which is the second definition. Okay, f of t tends to a, let's say this is a, as t tends to infinity, if and only if for every epsilon bigger than 0, there exists c such that if x is larger than c, then f of t and a are close within an epsilon of each other. Okay, so we could have something like this. Okay, you see the asymptote there. Here what we are saying, you just fixed here well, let's do it the proper way. So here we have our epsilon, okay, from A. And what we are saying is that there exists some number c such that whenever we are beyond that number c, t is beyond that number c. Actually here I meant t. There we go. Whenever that happens, we know for sure that f of t is minus a, that distance is less than epsilon in absolute value. Okay, and of course, we can do similar definitions for f of t tends to negative infinity as t to x, or f of t converges to a as t to negative infinity. Okay, it's just a simple adjustment. What we are going to do now is to reformulate the definitions we already have, to write them in terms of neighborhoods, so that we don't have so many different definitions of convergence. Okay, we will have a general framework. For that, we need first to define what is a neighborhood of infinity. Okay, we already know that an open interval is a neighborhood of a point. But what do we mean by a neighborhood of infinity or negative infinity? So here we have the definition. A neighborhood of infinity are all the points x in the reals that are bigger than a given constant, and a neighborhood of negative infinity are the points that are smaller than such constant. Okay, so we can write it as an open set C infinity or negative infinity C. Okay, these are half lines. Okay, half of the real line. Now with this definition, we are prepared to state the definition of convergence in general for the extended real number system. The precise definition is given here. Okay, here we have a function f defined in the domain E, a real function. And we say that f of t converges to a as t to x. And here a and x are in the extended real number system. So they could be numbers, they could be infinity or negative infinity. Okay, so we say that there is convergence if for every neighborhood u of a, there is a neighborhood v of x. Okay, these neighborhoods need to satisfy a couple of things. Of course, v needs to intersect e, and f of t, for every f of t that is in u, t needs to be in v intersection e, be different from x, but that's it. Okay, here we are saying that neighborhood u of a, there is a neighborhood v of x. So this is the role of our epsilon, this is the role of delta. With this definition, we can repeat the proofs we have seen so far, and we can handle the cases where we need to extend the real system.